Hi guys, Miss Burns here. We're going to take a look at section 9.6, which is our last section for this unit. And we've got two more tests for checking to see if a series converges or diverges. One's called the ratio test and one's called the root test. So the ratio test goes like this. Let sigma a sub n be a series with non-zero terms. What's nice about the ratio test is this will work even if you have negative terms. So this will work on the terms on a series where the terms are either positive or negative. If you take the limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term, so the ratio, where the name comes from, of the n plus 1th term over the nth term, if you take the limit of that as n goes to infinity and you get a limit that's less than 1, that tells you that the series converges absolutely. If you take that same ratio and get a limit that's greater than 1 or going to infinity, that tells you that the series will diverge. If it happens to be that you get 1, the test is inconclusive and you'd have to fall back to something else, maybe a limit comparison test or something along those lines. So let's look at an example. So determine the convergence or divergence of this particular series. So one thing I want you to kind of think about is all the tests we've done so far. We're at the end here. We've learned all these different tests for converging and diverging. You always want to try like the nth term test and see if that gets you somewhere. If that doesn't work, check to see if maybe it's geometric or telescoping. If that doesn't work, it's not one of those, then you've got a whole bunch of other things to choose from. If it's got negative terms, if it's an alternating series, you could perhaps use the alternating series test. If it's a p-series, you could use the p-series test. If you want to integrate it, you could use an integral test. This would certainly not be a good candidate for that because you've got this factorial here. And then we had direct comparison and limit comparison. We could perhaps use one of those, but oftentimes when you have a factorial, I find the ratio test is a good option. So let's go ahead and set this up. So the ratio of the n plus 1th term over the nth term, and make sure you see where I'm getting this n plus 1th term. Essentially, the n plus 1th term means if I take the series itself is the nth term. If I replace all the n's with n plus 1, that gives me my n plus 1th term. So I have 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. So what we have here is a complex fraction. And so to simplify a complex fraction, remember we take the fraction in the denominator and we use its reciprocal and change it to multiplication. And for most of these, you're going to simplify and look to see what it is you can cancel out. So if I have 2 to the n plus 1 over 2 to the n, well, remember 2 to the n plus 1 is 2 to the n times 2 to the first power. So those 2 to the n's would cancel out. And then remember also we talked about simplifying factorials earlier. I think it was at the beginning of this entire chapter. And we said if you have n factorial over n plus 1 factorial, remember n plus 1 factorial could be written as n plus 1 times n factorial. So the n factorial cancels and you're left with 2 over n plus 1. So now what is the limit of this as n approaches infinity? Hopefully you see that that's 0. And since that's less than 1, that tells us that this series converges by the ratio test. Remember, I always want you to give me a reason for how you know it converges, what test you use. You don't have to say absolutely here because this series didn't include any negative terms. It wouldn't be a problem if you said it, but it's just not necessary. Let's take a look at another example. So we want to look at the convergence or divergence of this series. And a lot of times when you have a really complicated algebraic expression, using this ratio test is your best bet. So let's go ahead and get this set up. A lot of stuff going on here. Let's break it down. I think you can handle this algebra. It's just a matter of getting used to the setup. So we have the n plus 1th term will be n plus 1 squared times 2 to the n plus 2. Make sure you see where that's coming from because the original sequence had n plus 1 in this exponent. So if we replace the n with n plus 1, that's n plus 2 over 3 to the n plus 1. And then all of that goes over the nth term, which is the original sequence itself. I'm going to flip this and change this to multiplication, flip the second fraction, change it to multiplication. I went ahead and dropped the absolute value because I don't really need that here since all the terms are positive anyway. And then start looking for things that divide out. So notice how I wrote 2 to the n plus 2. I wrote that as 2 to the n times 2 to the second. And so I have 2 to the n times 2 to the second. Here, let me back up a little bit. 2 to the n times 2 to the second 3 to the n plus 1 I wrote as 3 to the n times 3 to the first. And then here's the reciprocal of that denominator term. So you notice this 2 to the n will cancel with this 2 to the n in the denominator. This 2 to the first will cancel with one of these 2's here. And this 3 to the n will cancel with this 3 to the n here and leave me with another 3. So what am I left with in the numerator? I'm left with 2 times the n plus 1 squared. The denominator, I'm left with 3 times n squared. Now take the limit of this as n approaches infinity, and you can see this is a very straightforward limit to evaluate using the ratio of leading coefficients. Because the degrees are the same, we get 2/3, which is less than 1, so this series also converges by the ratio test. How about this one? We have n to the n over n factorial. So again, if you have some unfamiliar terms, if you have factorials in there, if you have a lot of weird exponents, that's when the ratio test might be a good bet. So let's go ahead and get this set up. Okay, so our ratio looks like this. The n plus 1th term becomes n plus 1 to the n plus 1 factorial. I'm sorry, just to the n plus 1 over n plus 1 factorial. The nth term is n to the n over n factorial. Okay, so here we have that expression when we use the reciprocal. So we have n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. So n plus 1 to the n plus 1 can be separated as n plus 1 to the n times n plus 1 to the first power. And remember, n plus 1 factorial is just n plus 1 times n factorial. So look what happens here. We have the n factorials will cancel, and then the n plus 1 in the numerator with the n plus 1 in the denominator here will cancel, and we're left with just n plus 1 to the n over n to the n. And so now, this at first looks kind of like a limit we're not able to do, but this is actually one we've seen before. We did it very briefly back when we talked about L'Hopital's rule. And please remind me on Friday, let's go over this again as a group so you can see where I'm getting this from. But if you simplify n plus 1 to the n over n, and you make that one fraction, so you write it n plus 1 all over n to the n power, and then separate that, you have 1 plus 1 over n to the nth power. And if we use L'Hopital's rule, this is actually an indeterminate form, 1 to the infinity. But if we use L'Hopital's rule and simplify, believe it or not, this limit will be e. And you probably don't remember how I'm getting this, but we'll go over this again on Friday in the office. Don't let me forget. But the point is the limit is e, which is 2 point something, and that's greater than 1. So what does that tell us about the original series? That tells us that this diverges by the ratio test. All right, and I think I got a little ahead of myself in the PowerPoint. There was an example 3. I'm going to skip it for now. I want to go ahead and talk about the root test. So the root test, again, works for any series, whether the terms are positive, negative, does not make a difference. But it says that this will converge absolutely if we take the nth root, the limit rather, as n goes to infinity, of the nth root of the absolute value of the sequence, the a sub n term. If that limit is less than 1, then we have a converging series. So the parameters are similar to what they were for the ratio test. The difference is what limit we're actually working with. If that same limit, the nth root of the absolute value of that sequence, if that's greater than 1 for that limit, or goes to infinity, we say the series diverges. And again, if that limit happens to equal 1, the test is inconclusive, and we have to fall back and use something else. So let's try this one, determine the convergence or divergence of this series. So a time that, or I guess a clue that it would be good to use the root test is if you can raise something to the nth power. When you have n powers that you can use for your term, that's probably when you want to use the ratio test. And so in this case, why does that apply? Well, I have e to the 2n, which can be thought of as e to the second raised to the nth power, right? E squared to the nth power over n to the n. So I can put all of this e squared over n inside the argument here and raise it to the nth power. So what I have now is an nth term that's being raised to the nth power. So if I take the limit, the nth root, the limit of the nth root of that sequence, I have the limit of the nth root of e squared over n, all raised to the nth power. So the idea here is what happens to these n's? They're going to go away, and I'm just left with the limit as n goes to infinity of what's on the inside. And so what is that limit going to be as n gets large? That gets smaller and approaches 0. So since that's less than 1, what does that mean? That means the series converges, and our reasoning would be by the root test.